Okay, good. We are 3 minutes late, but I put my timer, which means we will anyway finish 1 hour and 30 minutes. So as already Benjamin said, basically each of the mini course that we will be giving during these weeks, during this first week, it will be basically based on 4 lectures, each lecture 1 hour and a half. But since there are many things to say in general, what I will try to do here is to make it look like longer. So we'll try to do 8 lectures, which means 45, 45, 45, 45, and so on. It means that every 45 minutes we'll stop for a couple of minutes, and then hopefully I will manage to cover really what I want to cover in each block of 45 minutes. If not, I will take more time. And more time I mean to say what I want to say within the 1 hour and a half. And okay, more people are coming. Yeah, no. And well, it's nice to see both students and also seniors. I can see Paolo here, and also Fawad, and also Hans, who is our webmaster at Nordita. And so, okay, anyway, the plan of the lectures that I will be giving here, as you can see from the title, is Introduction to Perturbative Quantum Gravity. And what we mean with perturbative quantum gravity is basically just take gravitational interaction and try to quantize it in the framework of perturbative quantum field theory. And of course, before even starting, I should tell you which type of convention notation I'm going to use. I will not say anything. I just wrote them here to not waste more time. Look at them. What is important is that I will use this signature for the metric, the mostly positive, and these units, which are the natural units, for h bar and c equals to 1, but I will keep g Newton different from 1. And in this talk, I will always work in 4 dimensions, which means 1 time and 3 space. So when I say perturbative quantum field theory, roughly speaking, what we mean is that we will have some Lagrangian formalism with a kinetic term and interaction terms, and the couplings in this Lagrangian interaction coupling are such that in some regime can be considered small, weak, so that we can make some expansion, some perturbative expansion. And this framework of quantum field theory, perturbative quantum field theory, has been very successful, I would say, to describe other interaction of nature, like electromagnetic, weak, and strong interaction. Indeed, the standard model of particle physics, I think we all agree that has been very successful so far, although, of course, there are things to improve theoretically, but I think experimentally, that's what we have at the moment. Okay? If we don't put gravity into the game. Now, the idea here is really take the same tools that we have been using for the interaction and try to use them for the gravitational interaction and see what we can do. Can we really describe quantum aspects of gravity in a consistent way or not? This is, let's say, the logic that we follow. And before doing that, I think it's useful just to fix some of the, just to warm up a bit. I think it's useful to, I don't know why there is this light here. I don't know if it's annoying for the online people. Is it readable? Okay. I think it's convenient to just have a very quick overview of some elements of perturbative quantum field theory and also general relativity, classical general relativity, that will be used on my mouth. That is okay. Now I have a big head, that's why. Okay. Better? Good. Yeah, actually, I can hear myself better even now. So the idea now is basically to start telling you some elements of perturbative quantum field theory that is good, I think, to review, because we're going to use these elements and try to see what happens when we apply them to gravity. Okay. And one thing which, in my opinion, is very important about the perturbative quantum field theory framework is that, given some principle, starting principle, this framework is very restrictive in terms of the type of theories that you can write down. Indeed, if we look at the standard model of particle physics and the quantum field theories that we have in the standard model of particle physics, we don't have much freedom to change these theories if we start from some principles. Okay, and the idea here is just to tell you which are these principles more or less, and see whether this principle can also be used to describe some quantum aspects of the gravitational interaction. Okay. And of course, we will not be detailed here, maybe not even very rigorously, just to give you the idea of what we want to use to write down then a quantum field theory of the gravitational interaction. I think one important point in quantum field theory that we know in the star model is that all the Lagrangians that we write down are local. What I mean with that, basically, is just that the bare Lagrangian, so the one that you have before including quantum corrections, is basically a function of the field, where field can be some any tensorial field you want, and it can have derivative acting on the field, but up to some finite order in general. That's what I mean with the locality. So basically, we have some dependence that is polynomial in derivative. But this is already a good thing, because in this way, you are excluding a big class of theories, for instance, where in your Lagrange, you have some non-localities. For instance, exponential of derivative or 1 over derivatives and so on. And you don't put this in your starting Lagrangian. But of course, here you still have an infinite possibility of Lagrangian you can write down. What you also have as another ingredient, of course, are symmetries. And here you can have both external symmetry and internal symmetry. External symmetry, I mean like really symmetry where you make a transformation of your coordinates and see what happens to your field at your action. And at least when we work with quantum field theory in Minkowski space-time, we know that an important external group of symmetry is the Poincare group, which is basically just the combination of some Lorentz transformation plus some translation, where this lambda will be the Lorentz matrix. And this type of symmetry also very important, because also tell you that in your Lagrangian, in a way, you should have some structures that are invariant under this symmetry, okay, in your action. And most importantly, is tell you that, for instance, you should have order of time derivative and space derivative appearing with the same power. Think of boson equations or the fermion equation. You have one derivative of time and space, or two derivatives of time and space, and so on. Also, you have all the important things that come from this Poincare group, because thanks to the Poincare algebra, you can basically thanks to the Poincare group, you can basically also define tensorial fields, which are fields that transform in a certain way under this group. And you can also classify particles, because if you work in some representation, Hilbert space representation of the Poincare group, you can, for instance, introduce some invariant operators, which classify massive and massless particles. Indeed, we know that we can classify massive particle in terms of mass and spin. But if we have massless particle, what really matters in that case is the helicity. Okay. Now, we will not go into details. We'll just need some information that I'm telling you now. Later, we will really write down what is an helicity, for instance, and try to see what happens, for instance, in the case of the gravitational degrees of freedom. Okay, but these anyway are important symmetries, because they will constrain further your Lagrangian, because you should write down Lagrangian which are respecting the symmetry. And also you will have some internal symmetry, right? The internal symmetry group, where you can have, for instance, global symmetry. You make a global field transformation, or local symmetry, which is also called gauge symmetry, where you take the field and you transform it with some local dependence on space-time coordinates. And gauge symmetry is actually very important, although they are not really true symmetry. They are more like redundancy, because they are telling you that there is some redundant degree of freedom in your relativistic theory that you write down. Gauge symmetry are very important to constrain your Lagrangian as well, because, for instance, if you want to write all possible interaction between photon and electrons, you will write terms which respect this type of gauge symmetry, abelian gauge symmetry. For instance, in the case of, if you just take a photon and an electron, I emphasize the bar, of course, we know that we can write some Lagrangian where there is a kinetic term for the photon, a kinetic term for the fermion, and then we can add this type of interaction term, which are compatible with the H transformation for the field A mu, which should be some constant function of gamma. And then you can transform psi in exponential of I lambda x and psi bar exponential of minus psi lambda x. And you know that this type of interaction will basically give you some Lagrangian invariant in this transformation. But also you could add, for instance, an interaction term of this type. Where you have this combination of gamma function, f mu, which is the strength field. And this will be still some interaction term that is gauge invariant. But you cannot write down things that have, for instance, a mass term for the mu, because this will not be gauge invariant. Okay, so somehow symmetry is also important to restrict the type of Lagrangian interaction term that you can write down. It's always important to have principle because they tell you they reduce the number of possibilities you have. So less possibility you have, better it is, because you have a more unique way to select theories, use them to make to do prediction and test them with the experiment. Okay. And this is locality asymmetries. Then another important point is unitarity. And with unitarity, what I mean here is basically just conservation of probabilities. Unitarity is nothing to do about the sign of a probability. It's just a statement of conservation of probability. And yeah, good. And let's just briefly mention something about unitarity. So what I mean with unitarity is the following. Let's suppose we are in some kind of field theory, and we have basically some Hilbert space, physical Hilbert space, and we will have some final state, for instance, from which we are evolving an initial state A. Okay, and we can define an evolution operator from t minus infinity to t plus infinity, which is the S matrix, which will tell you that this state A is evolved into a state B. Okay, and what unitarity says that basically probability has to be conserved, which means that the norm of this state must be conserved. So you don't want like information appearing from nowhere or disappearing suddenly. Okay, and if you just basically write this expression, the statement of conservation of the norm here means basically that the S matrix has to satisfy some unitarity identity. And usually it's convenient to rewrite this identity here in terms of the so-called transverse matrix. So basically you write the S matrix as a trivial part, which is the identity, and a matrix of this type. And you can see how this looks like just by placing this expression inside here. What you will get is basically minus t bar equal to t dagger t. And this is the so-called optical theorem in operatorial form. But usually in practice, this is very useless. We need to work with the matrix elements. So what we do to do that, basically, we just sandwich between two states. And here we introduce some completeness relation. For instance, let me just be sketchy here. Let's suppose we have a completeness relation of this type, where Cn are coefficient defined through this relation. Okay. If you insert this identity here, and you sandwich with these two states, for instance, B and A, what you will get is an optical theorem for the element of this matrix. So you will have B T A minus B T bar T dagger A equal to what? Sum over n intermediate states that you can have in the process. And then you have B T and N P A. And this is basically the form, let's say, of the optical theorem for the matrix elements. Of course, even this is not very explicit because one should introduce basically also this sum also contains integral over the phase space over the momenta. So more generally, one should write to be more specific. We will not need it here, but the identity should be written like sum over possible intermediate states, and then you will have. I'm just repeating things that for sure you saw in quantum field theory. We will have basically this sum is this object, okay, and here you will have these states that depend on the number of momenta KL, which are basically some intermediate states that are virtually happening in a scattering process, for instance. Yes. And what is important, just one thing I will mention about this unitary relation, as I said, is that has nothing to do with the sign of probabilities, sign of the norms. It's just conservation probability. Where does the sign comes in is in this coefficient in the end, because this is related to basically to the norm of the states. And what you usually assume in standard quantum field theory is that the sign of the norm is positive. Okay. So we take usually in quantum field theory for the physical states some Cn positive, assume positive norm for the physical states, and then we can normalize it for instance equal to 1. And if we do that, we can get, for instance, just by working this way, some constraint from unitarity on the positivity of the imaginary part of an amplitude. And this comes very easily. Why? Because, for instance, you can take a elastic process, which means that you have some initial final states which are equal in this case. And you see, if you put B equal to A, what you will get is basically that twice the imaginary part of this amplitude is equal to something positive. Okay. And I don't know, maybe I think in the next lecture we'll see that when people speak about positivity constraints from unitarity, this is more or less what they mean, because you can get some positivity constraint on the imaginary part of an amplitude when you have some elastic process, in this case, for instance. And of course, this must be satisfied if you have a theory, a quantum field theory. And that's what we would like to have also for a theory of gravity. For instance, the simplest case you can imagine to see whether this type of condition is satisfied or not is the simplest amplitude, like a free propagation of a boson from one point x to a point y. What is this? Is the propagator. And if you take the imaginary part of a propagator, which is usually defined with the minus epsilon prescription, with the final prescription, what is the imaginary part of this object? Well, using the standard formula given by this expression in the limit epsilon going to 0, this can always be written as a principal value minus plus I pi of x, delta of x, okay? And if we do that here, basically what we get is pi delta of p square over m square. So this imaginary part satisfies some positivity, some positive definite relation, okay, which is good for the propagators that we usually use in quantum field theory, okay? Now, so this is something to like also to have for a theory of for a quantum field theory of gravity, right? You would like to write something that respects also this type of principle, which is unitarity. Then, well, I didn't this, but once you put some final prescription here, what you're assuming basically also some arrow of causality, because you're assuming that positive energies propagate forward in time and negative energy propagate backward in time. The usual story with to basically understand the relativistic what antiparticle are, just some normal particle that propagate backward in time. That's the type of interpretation you usually give, but we don't need to go there. And in the end, another principle I want to mention, which is, I think, in my opinion, the most restrictive one that you can have in this case, is renormalizability. Now, normalizability doesn't mean that you can renormalize a theory only, because you can also renormalize theory that are not renormalizable. What we mean with renormalizability is that basically the theory can be renormalized with a finite number of counter terms, possibly at any high energy scales. And if we look at all interactions in the standard model, like electromagnetic, weak, and strong, the quantum field theories associated with this interaction are strictly renormalizable quantum field theory. What does that mean? It means that basically the dimension of the couplings that govern the interactions at a high energy is zero. So you have dimensionless coupling. Okay. Indeed, all the standard model of particle physics follow this principle of strict normalizability. Which says the following basically: if you have some Lagrangian with some kinetic term minus some potential term, okay, and the potential term will be schematically given by some sum of interaction where GI is basically the coupling, okay. Without going into much details, one can classify theories in this way. If basically there exists an I such that GI is negative, you will have a non-renormalizable theory. If for all I, GI has positive dimension, you have a super renormalizable theory. And if for each I, the dimension of GI is greater or equal than zero, but there exists at least one I such that GI is zero, you have a strictly renormalizable theory. That's what we renorm. Okay, let's see. That's what we usually that's how we usually classify the theory in terms of renormalizability. And it so happened that if you take just the standard model that we usually study in the textbook, we are in this class. Okay? And if you think actually this class is even more restrictive because saying that you want couplings that have dimension zero is much more restrictive of saying that you want couplings with positive dimension, for instance, because you can have dimension one, dimension two, dimension three, and so on. So strict renormalizability somehow is very restrictive because it tells you that couplings has to have a definite dimension. And indeed, if you do that, for instance, for QED, okay, and you say you want to write down a Lagrangian for QED that is respecting these properties, symmetries, unitarity, and so on. As I said, if you just stop at symmetries, you may have this type of terms, not just one, also this other one. But if you look at the dimension of these two couplings, this one has dimension zero, while this coupling here has dimension -1. So this is a non-renormalizable coupling. So if you want to follow this principle, you will remove this to write down a fundamental Lagrangian of electron and photon, for instance, and you would keep only this term here. So you see, requiring strict normalizability will somehow limit the possible interaction term that you can write down, given a certain number of space-time dimension, but you always work in 4 dimension, of course. So this was more or less the quick overview of like basic principle that we are gonna ask our quantum field theory, the gravitational interaction to respect in the following lectures. And I was very quick here. I hope that more or less these notions were clear. But if we're already clear, but if there are questions, please ask. Indeed, I didn't say that, but the more you ask, the better it is also for me. Because if there is something that I didn't understand, I will understand it better together with you. and we will be here for 1 week. So if you have questions, please ask. Is there anyone who is not familiar, by the way, with quantum field theory? Some bachelor, no? Because we had. Okay, good. Please. You are a master student. Okay. So this was a bit. Okay, it's fine. This part here, the last part. This one. Okay, no, basically, okay, here the message to get is the following: that you have a Lagrangian formalism. You can write down kinetic term and interaction term. And what happens is that in quantum field theory, if you compute some amplitude, right, or in some scattering amplitude between two particles, okay, you may have situation in which your computation gives some crazy infinity that a priori you may think like, okay, something is wrong here, okay, but actually it's not, because there are tools called that are based on the theory of renormalization, which tell you how to basically subtract this infinity in a consistent way, and actually subtraction of infinity is also the way you define your quantum field theory, and allow you to basically extract finite in the end prediction or finite computation result from this calculation, right? But in order to reabsorb these divergences, in general, you have to add the so-called counter terms, which would cancel some divergence. And in non-renormalizable theories, the number of counter terms that you need are infinity. For instance, if you take a theory like by this kinetic term minus lambda 5 to the 6, this type of theory is not renormalizable. And it satisfies this because if you look at the dimension of this coupling lambda, this is dimension -2. So it means that if you do a loop computation, okay, with this 1, 2, 3, 4, 5, with this type of theory, this computation of this loop will give some divergence, and this divergence can be renormalized. But you see, the counter term for to normalize this type of divergence will have how many legs? 8. Okay, so it means that to renormalize this, you need to add, I don't know, call it delta, a 5 to the 8 interaction. Okay, and so on. If you want, you will see that we need the whole tower. So here, the point is that I don't want this type of theories in these lectures. We would like to see whether we can make sense of theories which fall in this class. What is this class of theory? This class of theory is a theory where basically you have all a finite number of counter terms. For instance, a theory with 5 to the 4 interaction. Okay? Oh, sure. Here you mean what is the, so sorry, I thought it was, so what I mean with this notation is the following. This notation means the mass dimension of the coupling. So for instance, you see, sorry, I didn't say that, okay. You have an action and a Lagrangian here, okay? The action, if I work with h bar equal to 1, the action must be dimensionless in unit of mass. So when I write this, what I mean is that basically the dimension of the action is 0 unit of mass. Okay? The dimension of the x4 will be 1 over mass to the 4, right? So I would write dimension -4. Which means that the dimension of the Lagrangian must be dimension 4, because you want to cancel and get 0 dimension. Now, here, if you have a kinetic term of this type, 1 over x, which is the derivative, right, is mass dimension. 1 over x here, 1 over delta x is mass dimension. So phi and phi must have dimension 1, 1. If phi has dimension 1, here you will have, for instance, dimension 6. In order to have in the end dimension 4 in the Lagrangian, you must have lambda dimension -2. Okay, that's what I mean with this bracket. Sorry, I didn't say what I meant with that. But the whole point here is that we would like to have Lagrangians where at high energy, the relevant couplings are dimensionless. And we will see some cases at the end. Okay. I hope it's more clear now. So, for instance, if you take 5 to the 4, you don't need to add anything else to renormalize the theory perturbatively. Okay. Indeed, here when I talk about renormalizability, I mean perturbative renormalizability, which is this that I'm telling you here. But the next lecture will also, by Benjamin and Alessi, we'll also hear about something that is non-perturbative renormalizability, but here we're not saying anything. I'm not even an expert of that. Okay, now, these were just the elements that I want to give.
Luca,
yes.
There is a question online.
Yeah.
So regarding the unitarity of S matrix, can one impose such condition when S matrix is not itself well-defined, like in the case of algebraic quantum field theory used in quantum field theory in curved spacetime?
Yeah, so I mean, indeed, what I meant here, first of all, is that I'm talking about flat space physics. So basically, you have particles that move in some Minkowski background, and you're somehow neglecting back reactions. So you're not saying that you have some particle that will curve your Minkowski background. And this is very important because you can define, first of all, a global time coordinate. Indeed, when you have an S matrix, in this case, you just say that you're evolving something from minus t infinity, minus t equal to minus infinity, to t equal to plus infinity. And you can do that just because, I mean, globally, you can define your chart of coordinates. Now, in curved spacetime, this is usually not true. And indeed, I think there is a lot of, it's not even clear how to define an S matrix in curved spacetime, I think, up to my understanding. And I think there is some work where people try to define S matrix in the sitter, which is another type of Maxwell symmetric background. I think the simplest after Minkowski. But I think the current state is that people don't really know how to define the same concept as matrix we have here, also in a generic curved spacetime, for instance. Now, I don't know if there is some expert here on S matrix in curved spacetime. Maybe someone else can say something. But what I mean here is basically that S matrix needs, in this case, some global time coordinate. It's important because how we define X matrix quantum field theory is that you have an evolution operator defined at some initial time and final time, and then you take this time going to minus infinity to plus infinity. And you can do that just because you have one time coordinate that you can use to cover the whole space-time. Okay, so I think the current situation is that, looking also at the literature, up to my knowledge, is that people don't know even how to define consistently some concept of S matrix in the sitter. It's not even clear whether it does make sense to define an S matrix in the sitter. Okay. If you can have some states at minus infinity plus infinity, you can connect. For sure, you can define some evolution operator at finite times in some way, but even there, I don't have much to say. Yeah, please. Asymptotically flat, of course, yeah.
That's all I wanted to.
But also in that case, of course, you may think like some scattering black hole space-time with some asymptotic flatness. Yeah, but even there, you must have define some like you cannot work like on a single chart, right? You have to say anyway what happens close to black holes and so on. You will have some, let's say, interaction region with some asymptotically flat Minkowski, but you will not be able to describe just a global, I think, S matrix this way.
What I meant is that this matrix cares about this.
Yeah, sure. Yeah. If you can define the same time coordinates that you can use. With wave boundary conditions. That's what I meant. Okay. But for instance, there is some construction of S matrix in a simple de Sitter, I don't know. It's not so there is no way even to think of that. Okay. So anyway, the current situation is that maybe if you have asymptotic flatness, you can do something, but I'm not sure even about that. But the point is that here, if you have flat space-time, you can do things. Okay. And you can try to do something more if you have some different curved space-time with some Minkowski region in some regime, in some distance scales. But I'm not sure you can really define like a global evolution operator and just take some limit of t going to minus infinity, t going to plus infinity in the same way we do it. That's why you cannot do it. Okay. Perfect. Thanks, Ivano. So the other one is, why is mass dimension an important aspect when talking about renormalization? Well, I explained it before. I don't know if it was clear because there was a question here inside the room.
In any case, we'll talk about that
Yeah, we'll talk
more
about it.
extensively
Yeah,
on
more
Wednesday,
extensively.
so
Okay.
it's fine.
Good. Okay, now we are more or less in time. So now the idea is just to go deep inside gravity. So yeah, I'm sorry if, I mean, for some of you these things are trivial that I'm saying, but it's good maybe to review some of the main aspects because we will repeat some of them for gravity. Now, yes, so as you can see here, there is some lecture notes which contains stuff, and we're not sent because they are not completed yet. And in these lecture notes, there are more information as compared to what you will hear during the lectures. Because the idea was like, okay, in the lecture we give some, we say things like the most relevant thing, and then we go and leave the details to people, to the lecture notes. And that's what I'm gonna do here, basically. For instance, in the lecture notes, you will find even like some discussion with the Einstein-Hilbert action where you also have a cosmology constant, but here we just avoid that. So the point here is that we assume that cosmology constant is negligible. So we are in a regime in which the cosmology constant is not important. Maybe on Earth it's not important, or some other places. And we'll try to understand basically quantum field theory of gravity in a Minkowski background in the same way we do with our interaction in the standard model. Okay. So what does that mean? To do quantum field theory of gravity, it means that we need to understand first what is the object we have to quantize. So what is the field that we have to quantize? And let's try to understand how to do that, what to do. So as we said, the theory that we would like to understand at the quantum level is the following. So this Einstein-Hilbert Lagrangian, where we have the Ricci scalar here. And we know that the field equation for this Lagrangian, let me define this kappa square equal to 8 pi g, right? Just to not carry this pi and g over. This, the field equation for this action, as we know, are this one, if you also include some matter, where the T mu is just defined in this way, my notation. And of course, we know that we have an action, we have some field equation, and we can also ask which are the symmetries that satisfy this action. And we know very well that basically action of this type are invariant under diffeomorphism. So basically, if we do a change of coordinate of this type, basically we should expect physics to be the same. And let's just focus on, for instance, infinitesimal diffeomorphism, where we say that we have some infinitesimal shift zeta of x, okay? And we would like to understand how, for instance, the metric component of g mu nu transform under this infinitesimal transformation. And we know already from GR course that basically, if you make this transformation, the metric would transform, you write it here, in this way. So we will have the covariant derivative like this way. So this is just the symmetrization here. Right. So for instance, if we make an infinite transformation and we check how the metric component will transform, they will transform this way. So it means that if we check the variation of this action with respect to this transformation, we should have some invariance of the action. And indeed, if we just take the variation of the action with respect to this infinitesimal transformation, what you will get is basically something like this, right? I'm just expanding, nothing more. And this is equal to what? Well, these are just the field equation, right? So what we get here is the following. Mu. And the variation here is basically what I wrote before. Okay, now integrating by part, okay, using symmetrization of the Einstein tensor, what you will get basically is 1 over kappa square current derivative of G mu. And of course, this is nothing what we know that this satisfies some Young identity, and this is consistent so with the invariance of the action under infinitesimal diffeomorphism. Of course, you can do the same also for if you put the matter action. In that case, what you will get basically is that the stress energy tensor must be conserved, covariantly conserved. Okay, these are just classical things. And what about the case of freedom? We know that G mu nu is a symmetric tensor with two components. It's a symmetric tensor with two indices. So in general, it's a matrix 4x4 matrix. It will have 16 components, but with symmetric, so 6 go away, we are with 10 components. But we know that we have some symmetry here. Let's call them gauge symmetry in the theory. So we should expect that some of the degrees of freedom are redundant. Okay. And indeed, that's what happens. In the end, the physical number of degrees of freedom, so the physical, let's say, independent component of the metric are only 2. And, well, I think there is, let's just mention this and then we stop. There is a quick way, it's not really a complete proof, but there is a way to understand why we should go to 2 at the end. Because you see, first of all, you have the invariance and this transformation, but you have 4 functions here, right, which are arbitrary, because mu can go from 0, 1, 2, 3. These transformations in terms of metric components means this. Okay, so in principle, what you could do is like to choose some of the function zeta 0, zeta 1, zeta 2, zeta 3 in such a way that you can kill, for instance, some of the metric components. Okay, you have 4, so in principle you can kill 4 things. So you can go from 10 to minus 4 equal to 6. But usually when you have some symmetry, like gauge symmetry usually hit twice. So you should expect other 4 degrees of freedom to be lost that are not physical. And I think there is a way to see it more or less is the following, because you see, Young identity somehow is related to this invariance of the action and diffeomorphism. And if you look at the Young identity closely, you write it, for instance, in terms of partial derivative. Also, you decompose it in terms of time and space. And then you will have the gammas, the gamma G. So mu, rho, nu, plus gamma, nu, G mu, rho, mu. Okay, this is just basically the covariant derivative written. Now, you see, what is interesting here is that what you want to see as what we mean here with physical components is basically what are the dynamical components of the metric field that evolve under some second order field equation. Okay, so for instance, if you have some component that evolve with a first order time equation, that will not be a dynamical equation, it will be a constrained equation, which will basically constrain the components of your field. And so the question is there any component, because you need the Einstein equation have many components, right? Is there some component that is just constrained, is not evolution? Actually, yes, that's the reason why. I mean, one way to see is the following. Because you see, in general, G, the metric tensor, has two derivatives acting on the metric. Here we have another derivative, which is time derivative, acting on this, okay? So if G0 nu had two time derivative acting on the metric, here there would be three time derivative acting on the metric. But you see here and here, there cannot be three time derivative acting on the metric because this is partial and here you can have only two. Here you can have only two. You can have only two. So what happens basically is that the G0 nu, okay, G0 nu will contain up to one time derivative acting on the metric. This means that the equation Z0 nu T0 nu will contain no dynamics for these components. And therefore, so you have four constraint equation. So we go from T minus 4, 2. Okay, so in the end, we expect 2 degrees of freedom to be the physical ones. Of course, one has to show it more explicitly. And we will do that actually in the framework of quantum field theory. We'll see which are the physical degrees of freedom that propagate. Okay. So with this, I will finish some review of elements. Well, 46. I was doing 45, so 1 minute late. So with this, I would like just to stop for a couple of minutes. And basically what we have done was just to give some elements of quantum field theory. Maybe it was too fast, I think, but I hope more or less is idea. It's clear what are the things that I would like to check and apply also to a gravitational interaction quantum mechanically in the framework of perturbative quantum field theory. And the theory that we would like to quantize in this framework is basically this one, okay, which satisfies this property classically. And what we have in mind now, to be closely to the framework of perturbative quantum field theory, is basically take the G mu nu, expand it around some background in terms of some fluctuation, okay? And in the end, the object we're going to quantize is this fluctuation here. So which means that when we go, we'll never use this hat, but if you want to quantize the G mu nu, roughly speaking, what you will do here, you will have operatorial, some operatorial identity here, and some operator here, okay? And to do that, what we have to do is we have to expand in fluctuations, identify kinetic term and interaction terms, and then describe things in framework of perturbative quantum field theory. And most importantly, here, which is the simplest thing you could do to start understanding gravity, I think, is to specialize to background of Minkowski type. So basically, we consider metric fluctuation around Minkowski background. Okay, that's what we're going to do in 2 minutes. So if you have questions, or you want to run to the toilet, please, you can do that. Difficult to see screen. Ah, here, I mean, okay. 1, 2 minutes, just really to erase the stuff here. Yeah. Ah. Yeah. Okay. Okay, well. Good. So, before going to coffee break, in this 40 minutes, I have the timer here. We started 3 minutes late. We are 50 now. So in 40 minutes, the idea is the following. We would like to understand perturbatively which are the degrees of freedom. I told you that there are 2 degrees of freedom, right? That was just a non-perturbative argument that I gave. Here we work in perturbation. As I said, I will try to count degrees of freedom and really identify which are the physical components of the Graviton fluctuations. So as I said, what do we want to do? We want to expand. I will tell you now. In metric fluctuation around Minkowski, here I'm going to put this 2 kappa, where kappa is the same that is here, because it will be convenient to see that the kinetic term will be canonically normalized. So in the kinetic term, you will not have this kappa floating around. Okay, that's why we are putting there. And you can see if I do that, kappa, let's remember, kappa square was 8 pi g. Okay, so kappa has dimension of 1 over mass. If kappa is dimension 1 over mass, since eta is dimensionless, h must be dimension 1. Okay, so which is sometimes said that in 2 derivative theory, this h is canonically normalized. Okay. Now, what is the idea? As I said, we would like to take this fluctuation and really take the Einstein-Hilbert action and expand it. Like in terms of, as if it was a Taylor series, but since we have a function here, we will have a functional Taylor series. So there will be a 0th order term. There will be a 1st order term. There will be a 2nd order term. Einstein-Hilbert 2nd order term. Depends on this. Plus, plus, plus. There will be some nth order term. Blah, blah, blah. Okay. Now, what are these terms? Now, first of all, the 0th order means just basically take the action, evaluate it in Minkowski. But at least in this case, we know that R evaluated at Minkowski is 0. This is 0. Then we have the 1st order. The 1st order will be basically 1 over 1 factorial, because we are ever expanding. So it's 1 over the factorial. And then we have the y4, the SH G mu nu 2 kappa H mu nu. This is y, this is y. Now you see when you have a functional derivative, you must have another integral because this is y. Instead here we'll have an integral over x, for instance. When you integrate the metric, you have x and y will generate delta Dirac and so on. Let's forget about the delta Dirac delta, otherwise we go crazy. Let's pretend we take them into account. So what we'll get here basically is the field equations. And we need to evaluate everything at the background, right? If you do a Hilbert expansion. Right? So this is just a functional derivative at 1st order. The G mu is evaluated at eta, so this is 0 again. And so this is 0. So the first non-trivial term that we get is basically the quadratic one. And the quadratic one, again, you can do the same. You will have 1 over 2 factorial, you will have 2 powers of this. Then you will have let's write it maybe in functional form completely. We will have two integral this time. We'll have here derivative with respect to g mu1 u1 y1, g mu2 nu2 y2. Then one, we have two power of the perturbation as if it was a terrorist. I mean, because one is y1, the other one is y2. Okay. And you can do that for any order. So you can generate kinetic term for each mu nu and interaction term for each mu nu. Now, what we're going to do in these lectures today, we're going to focus only on the free theory, which doesn't have any self-interactions, which means we will stop at this order. And tomorrow, we will go to interactions, to self-interactions, which means we will take this theory and we would like to understand degrees of freedom, degrees of freedom at the free level, and propagator of the theory. That's what we would like to do. Yeah. Okay. Yes. Yes. Is this clear? Okay. But as you see, if you have internet and so on, blah, blah, you have so many, you should do things correctly by taking into account the Dirac delta that you generate when you open this integral and so on. To make it easier, we forget about this delta Dirac, okay? We just write this S2 H here, like 1/2, a second variation. Yeah. The second, no, sorry. No. 1/2, and then the second variation of the Einstein Hilbert action. Okay. If we do that, basically what we have, we take the first variation, and here there is 1/2 kappa square from the action, and we will have yes, product of variation. Okay. And then it will take the other variation here. What we'll get is right, the whole all the variation. Okay. It's with respect to the metric, yes. Yeah, it's like I'm doing basically this H mu nu, okay? So the delta G mu nu in the end will be the 2 kappa H mu nu. Okay, yes. Okay, and in the end you want to evaluate everything at the background, of course. Now you see, if you evaluate everything at the background, we know that R is 0, which is not variation. We don't take any variation of R. So this goes to 0. Let's just remove it. And we were left with these objects here. And now, of course, to understand how to write delta R, delta square root of minus G, and delta second of R in terms of H mu nu, we should basically take the Ricci scalar, take the metric tensor, and expand them in perturbation. We will not do that here, otherwise we will never finish. But just to tell you that delta square root of minus G, if you use this expansion here, will basically be kappa H, where H is the trace of H mu nu. Delta R will be 2 kappa times this combination of derivatives. box H, where box is the D'Alembert, right? That is defined this way. And then, of course, you should also write down the second variation for R, which will be proportional to H squared and kappa squared. Now, this is written in the notes in a couple of lines. We don't need to write it, but the logic is the following. You do that, you plug everything inside this, and you basically will get the quadratic action in H for the fluctuation. And what we get is basically the following. We have the following. Yeah. We have minus 1/2 rho h mu nu, rho h mu nu. You see, as if it was a scalar field, just now we have a tensorial index, but since you have tensors, you will have more combinations. Plus rho mu nu, rho mu, h rho nu. Then there is terms containing the trace, plus 1/2 del rho h, del rho h, and then minus del rho h del mu h mu rho. Voila. So these are the 4 terms that you get in the quadratic action in H and nu. Now, I hope the writing is clear. These are the terms that you have. And it's very convenient to write the action in a bilinear in a quadratic form, where you basically have like H kinetic term H, as we usually have, for instance, for a scalar field when we write phi box phi. We want to identify the kinetic term, the kinetic operator, sorry. Okay? And to do that, basically, we should integrate by parts. We put all the derivative and the structure that are not depending on H between 2 H's. And then we symmetrize everything because we want a symmetric 4-index operator, because we have something like this. 1/2, that's what you want to write. H mu nu, some kinetic operator. And now you can do that easily. Let me just integrate my part and symmetrize things. What is this kinetic operator? It's the following. It's equal to 1/2 eta mu rho eta nu sigma plus eta mu sigma eta nu rho times box minus eta mu nu eta nu rho box plus eta mu nu del rho de sigma plus eta rho sigma del mu del nu. And there is a last term, you can imagine what it is, because we need to have another type of symmetrization of this index, which is the following, minus 1/2. It has a similar structure like this one, but you don't want do you want to mix the mu nu and the rho sigma? You want to mix this combination here. So you will have mu rho del nu del sigma plus nu rho sigma del mu del whatever, no, del nu del rho, and I use which mu and nu. So sigma del sigma del mu plus eta nu sigma del mu del rho. Okay, this is the kinetic operator for this action. And it's just a matter of integration. And when I say that is symmetric, what I mean is the following. mu rho sigma is equal to nu rho. Rho sigma is also equal to mu nu sigma rho. And also equal is to exchange the pairs. Rho sigma mu nu. Okay? And you can check this very easily. Okay. Okay. So this is the quadratic action we would like to focus on today. Okay. There are questions. Okay. Anyway, let's. Of course, the first thing we can ask is what is the symmetry of this type of action? And we would expect basically some linearization of the symmetry theory here. Okay? Indeed, you can show basically that if you do this type of transformation, which is some linearized version of that one. So there, basically, kappa mu nu rho sigma h sigma is equal to 0. And basically, this is telling that the linearized version of the symmetry will see that also the quadratic order in H at the level of the action. And of course, this symmetry, this gauge redundancy, let's call it in this way, is suggests that some of the degrees of freedom, some of the components of H mu nu are not really physical. Okay. And we would like to understand really what is the number of independent physical components on shell. So when you see a gravitational waves that propagates, and you quantize it, for instance, what are the propagating degrees of freedom of these waves? Even classically, we can do it, and you can quantize these things, right? And to do that, for instance, what we can do, we can just look at the field equation, impose this gauge redundancy, and see what are the degrees of freedom. And that's what we'll do in these 20 minutes. Yeah, 20 minutes, 22, 20 minutes. Benjamin is German, he's very strict. Yes, but we started 3 minutes late. So let's, okay. No, but I will finish in this part in 20 minutes. So, okay, let's not forget the logic. We derived, we took Einstein Lagrangian, we are expanding in fluctuations, and then we said, let's analyze for today the free theory. Free theory means we neglect interaction term in H. Okay? So we focus on this Lagrangian, on this action. The field equation can be taken by varying basically with respect to H mu nu. And the field equation can be written, for instance, in this way, just without any matter. Okay? Let's make it more explicit because we would like to see what really this equation is. If we use the expression for kappa, let's write the field equation in this very nice form. H mu nu, rho, sigma. These are the field equation, right? Just plug it and you get it. Yes, sigma rho minus 1/2 rho H. It is one term. Then we have minus mu. By the way, mu rho H nu minus 1/2. Then nu H, and then there is the symmetric part. Nu H nu mu minus 1/2 mu H equal to 0. So you just plug it everything and you get this. Okay. Now I wrote it in this explicit form because you can see there are putting pen on my face. Because there are these three terms which contain the same structure, as you can see. Okay. And will be useful for in a moment. As I said before, these are field equations, and not everything is dynamical here. Because you see, you don't have just box acting on something. You may have contracted derivatives, some of the components will not be completely contained to time derivatives and so on. And also, if we solve this equation, we know that if we find a solution, let's call it H mu nu sol, this solution is not unique because you can always make a gauge transformation and go to another H mu nu, which will still be a solution. So you cannot find unique solution. So there is some redundancy. You really will do it to see what is the physical solution of the field equation that will propagate as a free gravitational wave, so as a free graviton in the case that we are considering here. And what we have to do in this case is basically to impose a gauge condition, like we do in quantum, as we do in electromagnetism and quantum electrodynamics. And there are infinite type of gauge conditions that we impose. And here we will always mention, both today and later, both now and later, covariant and non-covariant gauges, because I think they're instructive. But we will mainly do the computation with the covariant gauge. And the simplest gauge that usually people use, that you for sure have heard already, is the Donder gauge, which is the following. You see, if you impose this condition, which are 4 conditions, by the way, the field equation will simplify because this goes to 0, this goes to 0, this goes to 0. So you just get H mu nu minus eta mu nu box H 0, right? Not only that, if you take the trace, you will get basically box H equal to 0. So in the end, we can focus on this field equation. Okay? And again, the same story as we did before the counting, right? We should expect in the end to go to 2 degrees of freedom. Now, before going to details, let's just see the counting, how it goes. Here we have some gauge condition, which has 4 conditions. There's a gauge condition that has 4 components. So in principle, we would kill 4 components of H mu nu. So from 10, we go to 6. But then, as it happens for electromagnetism, this condition does not fix completely the gauge because there is some residual gauge. Okay? Because you can say, okay, can I still make a gauge transformation of this type? So go from 1H to a H prime, such that this condition is still satisfied, because you don't want to break the condition already imposed, otherwise you have some inconsistency. Because these are 4, you want this 4 condition. Yes, you can do that. And basically, you just say, okay, let's make that gauge transformation. Let's see how this changes, and let's impose that the variation is 0. So we have the possibility to make a gauge transformation and still preserve this. And this is true. This is true only if box C nu is equal to 0, right? Like it's easy, just take the variation of this, we'll have a variation of H here, plug it equal to 0, you will get this condition. And these are again 4 functions, 0, 1, 2, 3. Not only that, this zeta satisfies the same type of equation as H mu nu, which means that we'll have some wave solution, similar instruction as those of H, which will have, for instance, the same momentum that appear in the propagation, because the solution of this equation will be something like this. There will be some vector which is not dependent on position, which we call polarization tensor. And then there will be some complex conjugate of it. That's the simplest wave plane solution, right? But also for this one, you may have the same. Zeta nu will be some, let's call it R nu, which is a vector that does not depend on position, IPX plus complex conjugate. Okay? And most importantly, P square which is basically minus p0 square plus p vector square, is equal to 0. Okay, so basically this solution have some propagating wave with momentum square equal to 0. So we expect some massless propagation in the end when we go in full language of quantum theory. So we have here 4 conditions, 4 functions here to choose to cancel some components. Let's do it. And let's see what we get for each mu, or better for this polarization tensor here. So I would like to ask, what are the independent polarization tensors that we have in Einstein general relativity? It's convenient just to work in terms of polarization tensor, as I said, so we forget about position space, and we just go to Fourier space, basically. And we will have this object h mu, which has 10 components, because we have because it's symmetric. And we want to impose these 2 conditions. So, which means if we write the gauge condition, the Donder gauge, in terms of h, in terms of epsilon, the polarization is basically p rho h, p rho epsilon mu nu minus 1/2 p nu epsilon, where epsilon is basically the trace of epsilon mu nu. Okay, and these are 4 conditions again, right? Because nu goes from 0 to 3. And then we can always make some gauge transformation of this type, where we have più nu r nu plus I p nu r mu. I get I because basically the Fourier transform of the derivative will be I p mu. Okay, and p square, as we said, must be 0. And to make the analysis simpler, let's suppose that the momentum of propagation of this wave, let's rotate it along the zeta direction. So for instance, we take p mu equal to p0, 0, 0, p3. Okay, for simplicity. Actually, it helps a lot. Yes. Okay, let's just revise. Let's see where we go. Now you see what you have to do basically, you just have to explicitly write all these conditions in terms of in this frame, in this direction, and see what condition you get from here. And here you can say, can I use my gauge freedom here to kill some of the component of epsilon? Yes, you can kill 4 components with these. You can kill other 4 components with these, then use the symmetry, and you will kill even more components. And in the end, you will end up with 2 components. What are they? Okay, let's go quicker. It's good that I write the components so you understand what I mean. So for instance, let's take this is 1. Let's call it A and B. So A, so the Donder gauge written in this frame along the z direction. The 0, 0 will be about z. I mean, 0, 0 will be 0, 0 plus epsilon 0, 3 plus 1/2 epsilon equal to 0. Then you will have the 1 component in nu, which will be epsilon 0, 1 plus epsilon 3, 1 equal to 0. Then you will have the 2, which is epsilon 0, 2 plus epsilon 3, 2 equal to 0. And then the 3, which is epsilon 0, 3, epsilon 3, 3 minus 1/2 epsilon equal to 0. And voila. Okay? this is what you get. Just put this p mu there. These are the conditions you get. Okay. Now, as I said, we can use this R mu nu to do something. Let's use them. Okay. For instance, let's take the 0,0 component, which is plus 2i p0 r0. You can always choose r0, so r0, such that the new transform this is equal to 0. Why? Because you can choose r0 to be equal to minus 2i p0. Okay. And you can do that also for the other components. So in the end, you can kill 4 components for your polarization. And for instance, the R0 will kill this. The R1 can kill the 0,1, I guess. The R2 will kill the 0,2. And the R3 will kill can be used to kill the 3,3. And now you see you have 1, 2, 3, 4, 5, 6, 7, 8 equations that you can use to kill 8 degrees of freedom. And in the end, what will happen is that the only component that will survive are epsilon 1, which is actually equal to epsilon 2, minus epsilon 2. And then there will be epsilon 1, 2 equal to epsilon 2, 1 for symmetry. So only 2 components. Okay? So it means that if you just want to write the can erase this convention, right? We don't need them anymore. Okay. This means that the polarization tensor will be the following. Will be a 4x4 matrix, 0, 0, 0, 0, 0, epsilon 1, epsilon 1, 2, 0, 0, minus, no, sorry, plus 1, 2, minus 1, 1, 0, 0, 0, 0, 0. Okay, but actually, this can be written also in this way. It's 10 minutes, perfect. Let me introduce some polarization E plus nu plus polarization cross nu, where the cross is this one. No, let me first do the plus. The plus is this one. La, la, la. And then the cross will be the other one. 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 0, 0. Okay, voila. So basically we wrote H mu nu, or the polarization tensor, in terms of 2 independent components, expanding some, let's call it basis of polarization in this 2-dimensional, in this case of 2 independent one, okay? And this, in terms of gravitational waves, will tell you basically how the gravitational wave classically disturb some distribution of mass, like either transverse or like vertically, horizontally, and so on. But we're not interested in these classical aspects. We would like to understand actually what are the helicity that H mu nu of this type propagates, right? We know that the photon, for instance, propagates helicity plus 1 and minus 1. Why is that? Because what we usually say, let's take the let's make a rotation around the z-axis in the xy plane, which will be a matrix of this type, some theta angle around zeta. 0, 0, 0, 0, 0, right? Oh, sorry, this one, right? This is the rotation matrix from the Lorentz transformation. In the case of photons, okay, what happens is that if you act this on the photon polarization, which will have only one index, so for the photon, for instance, okay, for the photon polarization, you will get one with helicity plus one. You will get basically this photon polarization helicity are eigenstate of this matrix, eigenvector of this matrix, with eigenvalues given by 1 plus minus I theta, epsilon, right? And that's what we said. So we check how the polarization transform under rotation, and if they are eigenvector, they will be basically from the eigenvalues we can read basically the value of the helicity, right? Because here what we have is basically jz, which will be the third component of angular momentum. In the case of massless particle is conserved, so you can define it as a quantity to classify particles without mass. Okay, so we would like to do something similar also for the polarization tensor. So let's take this h mu nu here, or let's take these two. Okay, we can ask, are these somehow related to some helicity? Are these eigenvectors of helicity? 4 minutes. And the answer is no, because now you have two indexes, so you need to act twice with the rotation matrix and with this inverse, actually, you have to act. So what we'll have is something like this. We will act twice. And you may ask, for instance, for this one, is this something times h plus rho sigma? No, it's not. The same for cross. So these ones are not eigenvector of the rotation matrix. So at least in this basis, it seems like that we cannot really say anything about the helicity of these graviton fluctuations. But actually, we can identify the helicity by making a change of basis. So for instance, we can introduce this a minus plus minus 2, let's call it in this way, equal to 1 over square root of 2 e plus mu nu plus minus I e cross mu nu. If you do that, okay, if you do this transformation, so you go from this a plus and a cross to, from this e plus and e cross to e plus minus 2, what you will get is that R mu sigma R rho nu theta acting on these two type of vectors really gives something that is eigenvalues times eigenvector. And the eigenvalue is basically voila, this one. So from here, we conclude that the graviton that we are going to quantize in this theory of gravity, which is this free fluctuation, will basically propagate helicity plus 2 and minus 2. Okay. So you see, we impose the gauge conditions and we show that basically on-shell physics should not depend on this unphysical degree of freedom. And in the end, we got something which is very simple, right? Because we have only two independent components with some helicity. Just 30 seconds. Here I worked in a covariant gauge, but you can take any gauge you want, even on covariant. For instance, you can impose a type of Coulomb gauge that actually we will see also in the case of propagator in the second part of the lecture. For instance, you could impose, instead of the Donder gauge, this one with mu 0, 1, 2, 3. Is another gauge, it's crazy, right? Because you have something which breaks Lorentz invariance. You can plug it in the field equation. You can look at the field equation. And actually, you can see that by imposing this, which is for condition, looking at the field equation, you realize that there are some components which are not dynamical and some that are dynamical. And the non-dynamical one will basically be constrained equation and will give you all the four conditions. This will be in the notes, so you can check it later. The important point is that it doesn't matter which gauge you impose. On-shell physics is gauge independent. And indeed, as a nice exercise, you can check in the notes that if you do the same analysis with this gauge, you will get the same result. Okay. So with this, we will stop. We'll go for the coffee break. But if there are questions, by the way, yeah, either now or coffee break. Oh, now if you want. No, actually no, because this one will be. There is some. Is like the function that you have R mu will be a constant somehow. You cannot use it for 0 because there will be like when you impose the other gauge. When you impose the other gauge, you will see that basically your equation are fully dynamic because you just have box h mu nu. Okay, so there is still a residual gauge, which is indeed what we saw before. What happens in this case that if you impose it, okay, you will get some field equation which are not fully dynamical. There will be some components that are not dynamical. So you will see some residual of this gauge in the fact that you have some constraints component in the field equations. Okay. So it's different where the usually people say a gauge invariant hit twice, which is true, but this twice can have different way of acting, okay, depending on the gauge that you impose. And you will see the big difference, especially when you impose covariant or covariant gauge. Okay. Yeah. Yeah. You mean if you have a theory of gravity? No, we will always have this because if you have some action written in terms of like a metric and curvature tensor, like a theory of gravity with any type of, we will see an example at the end of the lectures tomorrow. You may we will always have this type of well, this is not here anymore. If you do like a different Physician transformation, we'll still have a symmetry of your theory. For instance, you can say I have an action like R plus R square plus R box R, whatever you want, anything you want, you will still have some gauge redundancy related to the diffeomorphism.
Like gauge transformation in this case. No? In GR, we can basically do gauge transformation.
It hits twice. You will have always some gauge condition plus some residual. Yes, but in higher dimension, you will have different number of helices. For instance, if you have d dimension, in d dimension, h mu is symmetric, so it has d 1 plus over 2 components. Okay. Then you will have a gauge condition which will go from nu to 0 to d minus 1, right? So d condition minus d, and you will have some residual which is minus d again. Okay. And if you look at everything, just to have things, what you will get is this number of helices. Yeah. For the photon, for instance, you have 4 components, right? Because you're a vector. 4, and you will have minus 1, but in d dimension, you will have d components. And then you will have minus 1 from the Lorentz gauge, for instance, minus 1 from the residual, because basically they are just scalar equation, they don't have components, and you will get d minus 2. Okay, so the number depends, it's different, but the symmetry is the same logic. I mean, you have some symmetry and you can use them to kill things. Yeah. Yeah. So basically, just we go for coffee break, but later we will discuss the propagator in different ways, in different gauges. Okay, you can go for coffee break.